Welcome to part 2 of week 8's lesson. After this lesson, students will be able to prove and apply the formula for the sum of an infinite geometric series. You may continue on your capture sheet from part 1 of the lesson. In the discussion, you were asked to consider this scenario. You have a sheet of paper. You tear it in half and give half to a friend. You tear the remaining piece in half to give to another friend. You continue this process of tearing the paper you have left in half and giving it away. Question 1. How long can this process continue? Well, you can theoretically continue to tear the piece of paper in half, smaller and smaller, forever. Practically, the pieces of paper will get tinier and more difficult to tear, but there is no smallest piece where the process stops. Now question 2. What if your friends returned all the pieces back to you? What do you get? Well, you would get back the entire sheet of paper. It just might be a difficult puzzle to put back together. Let's look at the discussion more visually and mathematically. You started with one whole sheet of paper. Then you tear it in half and share half with a friend. This is the first piece. Then you tear the remaining piece in half and share half with a friend, a piece that is a fourth of the original paper. You tear the remaining piece in half and share the third piece, which is now an eighth of the original paper. Theoretically, you continue this process. The second part of the discussion asked what you would have if your friends gave back all of the pieces. You would have all the pieces to reassemble and give you the whole one sheet of paper back. But how can the sum of an infinite number of terms add up to 1? We've just been exploring the sum of an infinite series, not to be confused with the limit of an infinite sequence you saw in part 1. In this part of the lesson, we will focus on what it means to find the sum of an infinite series. In last week's lesson, we defined a series as the sum of an infinite or finite sequence. We are now going to focus on infinite series and their sums. Again, let's formalize the language and use summation notation to represent the infinite series. Notice that the upper limit of the summation is now infinity, to show that the series continues without end. Also last week, we defined the sequence of partial sums and noted that each partial sum is itself a finite series. We will define the sum of an infinite series as the limit of the sequence of partial sums. If that limit exists, we will say that the series converges. If that limit does not exist, we will say that the series diverges. In other words, if the sequence of partial sums converges, the series converges. If the sequence of partial sums diverges, the series diverges. Now that we have a formal definition for the sum of an infinite series, let's apply the definition to our paper tearing scenario. Let's start with our original values from the tearing of the paper. These represent a sub 1, a sub 2, a sub 3, etc. in the sequence of terms. The first tear resulted in a half, the second tear in a fourth, the third tear in an eighth, and so on. What we are interested in now, though, is the sum of these values. The definition says we need to find the limit of the sequence of partial sums. The first partial sum is the sum of the first term. It's only one term, just 1/2. We add another term to get the second partial sum. 1/2 plus 1/4 is 3/4. And another term to get the third partial sum. 1/2 plus 1/4 plus 1/8 is 7/8. We can continue finding these partial sums as many times as we'd like. Here are a couple more. Now that we have several values, let's look at the sequence of these partial sums. The sequence of partial sums is 1/2, 3/4, 7/8, 15/16, 31/32, and so on. It looks pretty clear that the sequence of partial sums is approaching 1. Each sum is getting closer and closer to the value of 1. That means that the series converges to 1. And that fits what we already know, that putting the pieces back together would result in the original one whole piece of paper. This process works for any sequence, but it takes a lot of time. Is it possible that we could find a formula for the sum of an infinite series? It turns out that we can find a formula for the sum of an infinite geometric series. To do that, we will use the same kind of trick that we use to find the sum of a finite geometric series. Let's practice using the paper tearing series from our discussion. The common ratio is 1/2, so we multiply the series by 1/2. This shifts the series by one term, so we can line it up in this way. Now let's subtract. We notice like terms will cancel, but this time they continue to cancel infinitely many times. What are we left with? On the left side, 1s minus a half s is 1/2 s, and on the right side, the only term that did not cancel is the 1/2. Dividing by both sides of 1/2 gives us s equals 1, which is the same answer we got using the definition. Now let's generalize to any geometric series. Here is a general geometric series. Now multiply both sides by r. Again, the terms shift by one term. Now subtract. And see that all the terms on the right cancel except the first one. On the left we have s minus rs, and on the right we are left with the initial term a sub 1. We can simplify by factoring out the s on the left. Then we can divide on both sides by 1 minus r to give the final result. This is our formula for the sum of an infinite geometric series. Note how this expression compares to our previous formula for the sum of a finite geometric series. Let's try applying the formula to another infinite geometric series. Determine the sum of the infinite series here. Consider this infinite geometric series and the formula we just established. Pause the video and determine the sum on your capture sheet. The first term, a sub 1, is 4. And the common ratio, r, is 2 because the pattern is doubling or multiplying by 2 each time. We can now substitute those values in, and then simplify. We get the sum to be -4. But wait, do you notice anything off or wrong with our problem and the answer we got? How can the sum of this infinite list of positive whole numbers be -4? Well, let's think about this a little more. Is there any way at all that an infinite number of positive numbers can add up to a negative answer? No, it's just not possible. So what's wrong here? Why did the formula not work like we expected? Well, bizarre things can happen when we talk about infinite series. Let's take a moment and see why, and when the formula will or will not work. First, let's remember that a geometric sequence is modeled by an underlying exponential function. Even further, we must remember that exponential functions can grow or decay. Recall what each one looks like graphically. Based on the two graphs, which one do you think will converge and allow the series to have a finite result? The only way a series has a chance of converging and possibly adding up to a finite number is if the underlying exponential function is decaying. The terms in the sequence are approaching 0 very, very quickly like they did in the paper tearing discussion. The limit for the sequence must be 0. The limit of the sequence has to be 0 for the series to have any chance of converging, but that does not mean it always will converge. The exponential function we just saw in the previous example demonstrates an exponential growth function. The sequence is diverging, or approaching infinity. So we can't possibly add up an infinite bunch of big numbers and get something finite. So does the formula work or not? Or when does it work? At the very least, a geometric series only has a chance of converging if the underlying exponential function is decaying, in which case the sequence is converging to 0. But what indicates when an exponential function is decaying? Well, looking at the functions themselves will help. Consider each of the common ratios. An exponential function will decay when the common ratio has an absolute value less than 1, meaning -1 is less than r is less than +1. But does a geometric series with a common ratio between -1 and 1 always converge? So let's go back to our definition of convergence of an infinite geometric series. A series converges to the sum S if the sequence of partial sums converges. We have a formula for the nth partial sum of a finite geometric series from a previous lesson. We need to find the limit as n approaches infinity of S. The only place n shows up in the formula is the r to the n. We can focus on the limit of that part. The r is a common ratio, and r to the n is a geometric sequence. We just saw that the limit is 0 if r is between -1 and 1. So 1 minus r to the n approaches 1, and the limit of the sequence of partial sums is the first term, a sub 1, divided by 1 minus r. Here is the formal statement of our result. In the paper tearing discussion, r was 1/2, which is between -1 and 1. So the formula worked and gave us a sum of 1, the whole sheet of paper. In the second example where r was 2, the formula gave us a ridiculous answer because r was bigger than 1. Now that we have formalized our understanding of infinite geometric series, apply it here. Pause the video and determine the sum, if any, of these infinite series. Let's see how you did. Recall the formula for the sum of an infinite geometric series. Starting with a. The first term is 9, and the common ratio is 1/3. The common ratio is less than 1, so the series will converge and we can apply the formula. Simplifying gives us a result of 27/2 for the sum. Now on to b. The series in b is geometric, but the common ratio is 5. That is greater than 1, so the series diverges. We cannot find the sum. Finally, c. In c, the common ratio is 3/4, which is less than 1, so we can apply the formula. Since the series is given in summation notation, we must find the first term by substituting 1 in for n and simplifying. The first term is 8 times 3/4 to the first power, which results in 6. Substituting into the formula and simplifying, we find the sum to be 24. We've spent a lot of time talking about infinite geometric series in this lesson. What about other types of series? Do other kinds of series converge? What about arithmetic series? Well, let's see. Consider these two arithmetic series. Will either of these series converge? Since the series are arithmetic, the underlying functions are linear. Neither of the functions approach 0 on the right. The first one approaches infinity, and the second one approaches -infinity. So in both cases, the series will diverge. Try as you might, you can't find an arithmetic series that converges. so infinite arithmetic series are just not very interesting. But wait! What about the series 0 plus 0 plus 0 plus 0 and so on? Does that converge to 0? It seems obvious, but then again, what is 0 times infinity? Answering that will actually require a lot more background than we have right now, but it's an interesting idea to think about until then. If you take AP Calculus BC in high school or a second semester of calculus in college, you will study many more types of series using a variety of tools. You will even study how to represent common functions in series form. For now, we'll stay focused on geometric series with numerical terms. Now you can practice your new learning of infinite geometric series on Khan Academy and then take the Check for Understanding quiz on MyMCPS.